In this video, we'll focus on the concept behind correctly interpreting a p-value. So let's say Mr. Sager gives you a die to roll and tells you to roll it 120 times to test it out. Unbeknownst to you, Mr. Sager has altered the die with undetectable weights so that it produces sixes 1/3 of the time instead of 1/6 of the time. You roll 37 sixes out of 120. Have you collected enough evidence to identify the die as being unfair? This is a yes or no question. That makes it a hypothesis test. There's one sample, it's a proportion problem, so we have a one proportion z-test. Null hypothesis is that this die is producing sixes at the expected 1 out of 6 probability. Alternative is that we're getting sixes at something other than 1/6 of the time. We check our conditions, we get a z-score of 4.16, that's pretty unusual, and a corresponding p-value of 0.00003. So based on that, we'd reject the null hypothesis. Our p-value is very small. There's sufficient evidence to suggest that the die is unfair. So here are the key things from phantoms that we're going to use to interpret the p-value. So our p-value is 0.00003, and it's telling us what's the probability of seeing what we saw in our sample, namely that we roll 37 sixes out of 120, if the null hypothesis is true. This is a conditional probability. Out of context, we can interpret it as, given the null hypothesis is true, the probability of seeing the observed statistic or more extreme is 0.00003. In context, if the null hypothesis is true, and there's a 1/6 chance that the die roll will result in a 6, the probability of a result equal or more extreme to 37 sixes out of 120 is 0.00003. In other words, with a fair die, this result would only occur once in around 33,000 trials, and that's why when we reach this conclusion, we say this is probably not the actual proportion of sixes that we'll be getting. The null hypothesis is rejected, and we conclude that there's something other than 1/6 for the actual proportion of sixes. As for where this number came from, 33,000, it's just 1 over our p-value. That's telling us how many trials we would have to take to see one instance of 37 sixes out of 120 or more. So we got a really unlikely p-value. It was 0.00003. It would pretty much never happen with a regular die to get that many sixes out of 120. Now, the way that you guys tend to interpret a p-value incorrectly is you write something like this. The probability of getting 37 or more sixes out of 120 is the p-value. That's not correct, and the reason it's not correct is the only way that this is actually accurate is under the assumption that the null hypothesis is true and that this die is a fair die that's going to produce sixes 1/6 of the time. Now it tells us in the problem that you don't know it, but I've changed this die so it's not producing 1/6 sixes, and instead it's producing 1/3 sixes. So with that in mind, how many sixes would we expect to get from 120? Well, we'd expect to get 1/3 of 120, which is 40. In actuality, we got 37. That's really not unusual. Okay, so the reality of the situation is that this die is going to produce 1/3 sixes. Okay, our alternative is that it doesn't. Okay, and if we ran the hypothesis test under those two hypotheses, we would get a p-value of 56%. So in other words, under the assumption that the die is fair, our results are incredibly unlikely. We would never see that many sixes. Okay, but under this new reality, the fact that I've changed the proportion of sixes from this die to 1/3, our results aren't unlikely at all. In fact, we would see them more than half the time. More than half the time we would get something that was as far from our expected value of 40 as 37 was. Okay, the p-value is not the probability of observing the results of our sample. It's the probability of observing the results of our sample under the assumption that the null hypothesis is true. Okay. Now, the other thing to mention is that we always have this or more here, and that's because any time that we find a test statistic, we got that z-score, we always compute it out to the edges. So this here would be 37, but then we say or more extreme because we're also going to the right or to the left. This was actually more than, because it was on the high side of 20, so that should be over there. All right, but so that or more means that we compute our probability out to the tail.